they'd like to share in front of their colleagues publicly, they have an opportunity to do so. And so we do have some updates to share. I think first is Richard. So without further ado, Richard, please go right
All right,
ahead.
let me share screen. Share screen. Okay, you guys see that?
Yep.
Cool. I'm gonna quickly go through this summary, but not go into much detail. This was a summary for Stephen and Joel, just going over the project. So it was and really a rough overview of everything. So talking about moduli spaces, deformation theory, graph edit distance spaces. Oh, sorry. Yeah, this incremental graph growing thing and how there's happens to be a Wolfram model that corresponds to it. And I was thinking today, what's the hypergraph equivalent of this? And could you find a Wolfram model equivalent of the hypergraph incremental growing system or whatever? Yeah, graphon spaces, graphon moduli space, graphon estimation, self-similarity, which we didn't do much with because, yeah, this Kronecker fitting thing is maybe not as maybe not sort of developed idea. And yeah, then the whole Fractron, like here you have some space of programs, these lattice structures that each program sort of creates and so forth. That's really the summary I want to. Sorry, it's just loading as I'm scrolling. Oh yeah, and then like graph signals, so sort of projecting the the vertex values onto some sort of eigenvalue bases of the adjacency matrix, and gives you this kind of idea of a Fourier transform on graphs. Instead of a one-dimensional, say, audio signal, you can do so on graphs. And although I didn't sort of find anything too interesting there were some, yeah, for example, like this program here has this sort of sharp cutoff. The others have like more of these resonances rather than, but whatever. And then, yeah, self-interpretation, that was another thing. This whole idea of a catalog number. So there's a unique number for every general recursive function. Kind of interesting that you could have this kind of library of Babel kind of thing for all programs. And then the entropy idea, which the suggestion from Carlos was this idea of relative entropy. So you would take some kind of ratios of these rather than just looking at their absolute values. And then finally the idea of sort of rewriting rewrite rules as a sort of way of endowing Rullial space with some topology connections with, say, inductive logic programming, which is where another place where meta rules show themselves. And this nice paper here, Geometry of Program Synthesis, which talks about this sort of continuous relaxation of a Turing machine. And they have this statement in there that programs are singularities of analytic varieties, which I thought in itself as a kind of soundbite is an interesting way of maybe leading into other areas of mathematics. And then I left some unrelated stuff that I'd done. I did some like random rule 30 thing. This is this neural thing. And this is, anyway, these were just like my side projects that I happen to have done recently. So this has opened some questions about sort of spaces of programs so an idea from Stephen was to look at neural networks. So like taking a sort of journey in weight space as being in some ways another way of thinking about sort of traveling in Rullial space. So I've taken Stable Diffusion, although some optimized version so that it can actually run on my laptop. It uses a lot of VRAM, so this optimized version keeps only what's necessary, and it uses half precision floats and things like that. And yeah, I did some experiments. So first we want to check for determinism. So yeah, Stephen had made this claim that some things were sort of non-deterministic, but that's really down to some sort of some missed opportunities for synchronizing things on GPUs. So yeah, floating point arithmetic is not commutative. So if you do things in different orders, you get different results. So in sort of straight up mathematics, you would get the same answer, but in computer floating point world, you sometimes don't get the same result. So it's things like ChatGPT at zero temperature will give you different outputs, and it's really just a bug rather than some ghost in the machine or something. So here I just and Stephen suggested sorry, a cat, but I thought a wolf was more appropriate, for branding or something like that. Anyway, so multiple runs with the same seed results in a zero difference between the two images, and that's cool. And yeah, this is this in-depth review of deep learning non-determinism. It's a whole massive PDF with all of these issues and why the problems happen. PyTorch is really good. TensorFlow had some problems with determinism. So let's take a journey in weight space, and let's do that by. So the seed that we're using influences the stable diffusion generation process. So we always get the same image, but it also affects the noise that I'm adding to the network. So it's like I always get the same noise vector. So we're kind of moving in a sort of linear span, a sort of subspace in weight space kind of thing. And it does some interesting things. So here we get this wolf, and then like, oh look, his legs have gone weird, and like, what's this? Like why is he sticking his leg out? And then he gets a kind of weird derpy face in one of these frames where it's like he looks kind of a bit like that meme bad taxidermy. There's one of these frames here where he looks a little bit like bad taxidermy. I forget. I think it's this one. Or anyway, sorry, I'm afraid to click. I just clicked something, so sorry. We're gonna have to wait a second because this is all right. Okay, right. And then interesting things are happening. So like here, it's like his mouth's open, and also it's going grayscale. So the grayscale thing is not massively surprising because what we're doing is we're sort of messing up that final convolution, which has three channels for the different color channels. So we're making those less distinct, I think. I think that's why we're seeing some grayscale things. And yeah, like the wolf also gets like very close to the frame, which is another weird thing that I didn't expect to see. Although, yeah, what's interesting here is that his eyes have gone grayscale, but then for some reason they become yellow again in a weird way. And then, I don't know, he kind of starts to lose features. And then at some point, there's like a phase transition, which is so random. And now it becomes this silhouette. And I did not expect such a kind of graceful degradation of this stable diffusion model. But what's interesting is I think this is a property of adding the Gaussian noise. So I would have expected it to just go doing weird, crazy things, but actually it sort of gracefully degrades. So it's like going.
Richard,
yeah.
can you? I mean, for my benefit personally, and probably some of the viewers.
Sure.
Could you flesh out a little bit what's going on behind the scenes? Because you said it, but like.
Okay. Yeah, sorry. So we have stable diffusion, and all I'm doing is I'm adding noise and then sort of gradually scaling that noise to the parameters of the model.
So could you remind us like
what stable diffusion is, or how?
Yeah, like the model a little bit, like some of the characteristics,
yeah. Cool. So, I mean, the idea, it's sort of based on this non-equilibrium thermodynamics kind of picture where, and there's a lot of very interesting details. I sent a few references to Stephen, and I mean the idea is that sort of during training we're trying to sort of turn the world into noise, but at the same time we've learned another model in the other direction to go from noise to some sort of sample from our distribution from the training data. So there's sort of two things going in parallel, and you have this text conditioning as well. So you have like a small language model, a transformer network, which is sort of taking a sentence and embedding it into some sort of latent space, and that conditioning is influencing the diffusion process. And the diffusion process at inference time takes some Gaussian noise and then sort of basically denoises it over and over and over. You can think of it as kind of following a gradient or some kind of optimization procedure as well. The network they use is called UNet, which is a sort of particular architecture that has these, it's not important details, but it has these skip connections, and it has like, lots of different convolutions of different sizes. Essentially, it's just some kind of denoiser image model. UNet gets used in all sorts of places. They even use it for segmentation of like brain scans and things. And there's all sorts of applications for the UNet architecture. So yeah, so UNet is predicting some kind of perturbation of the noise to bring it. And yeah, they also think of this thing as some kind of stochastic differential equation as well. That's another way of looking at the yeah the image generation process. We're sort of evolving some stochastic differential equation, and it's taking us away from this normal distribution to our data distribution, conditioned on the text latent. So yeah, that's it. So start from noise, and then over, in this case, about 45 steps. You're sort of running the network again and again and again, and it's like adjusting the pixels, and it's all very probabilistic. So the output of the network has some sort of sampling step, and there's a lot of feedback. So it's like looking like, oh, what does it look like now? Okay, I need to add this noise. There's also a noise schedule. So per iteration, the noise is getting less and less and less and less and less. And yeah, there's a, I don't know how much more sort of complexity or detail, I mean, of the model I should go into, but that's the general idea of diffusion.
Sure. And then
Yeah.
so what's being changed here? What is it that?
So what's being changed here is like the parameters of the neural net. So the connection strengths between the neurons, and then the biases for individual neurons.
And those
In
are the
this
things that
experiment
are
here,
those are the things that are largely determined by training, right?
those are completely determined by the training. Yeah. I mean, they're randomly initialized, and then during training, the network falls into some sort of basin of attraction or whatever you want to think of it. Although I did find a paper that said they don't actually fall into fixed points; they're always sort of moving. But whatever. So, like, the network ends up in some place, and yeah. And what this is showing here is if we move in some kind of like direction away from where the network ends up, then obviously we see some degradation of the output. But as stated, I did not expect the degradation. Let's do the animation. So I didn't expect the degradation to be so kind of graceful along the way. Like, why didn't it turn into skyscrapers or I don't know, giraffes or so? Do you know what I mean? Like, because yeah,
Yeah.
I'll show you later that there's some other results which
And so okay, so I mean, as you mentioned, this modification of the weights is some kind of subspace,
yeah,
some
exactly.
kind of
Linear span, like or just multiplying a vector
yeah.
by some number of times. Yeah.
So is it right to think that you're somehow preserving like the subspace, but you're actually modifying the vectors within the subspace or something like that? And that's why. 'Cause I mean, is it
yeah.
how surprising is it that by changing? I mean, how? I mean, what is the change that is being applied to these values? Like,
Okay, so for every block of parameters, I take the variance, and then I take some normally distributed values in the same shape of that weight matrix, and then some scale factor that's global. And I do this for every block of parameters. I do it for the weights and biases. So for a set of weights or a set of biases, I compute the variance. Then I have some noise vector, which I multiply this variance, because I start with unit variance Gaussian noise, so I multiply the parameter block variance with that, and then some global scale factors, which is what I'm incrementing gradually
sure.
across the whole thing. So actually, I'll jump to the other results, and then we can compare with this one. So I mean, here is the same idea, but just a different prompt. So like, I've changed the prompt to a photograph of a pack of wolves, and you see a similar thing where like, it's the same kind of degradation. Let me just jump to the video because it's running slow. So we get this weird kind of, it goes grayscale. There's some changes to the structure, and then it goes kind of cave painting like, and then it sort of disappears. And yeah, then I'm doing a bit more surgical thing. So I'm starting to go sort of into, rather than over the whole network, let's look at sort of individual modules. The network actually has a few different sort of modules, and then there's sub modules and sub module, and so I start by just going one level down, and we get this, which doesn't have the grayscale, effect, but has sort of similar changes to the output. Again, the same the same thing. And here's where I think it gets a little bit interesting in relation to your question is if the noise becomes sparse, uh, well, in this case, at around 50% sparsity, we see the biggest change, which is it sort of becomes a bit more like painterly. So and on either side, it looks kind of photorealistic. And yeah, and in this case, I actually got complete. And if I restrict the noise to the embedding weights, which is basically for every sort of token, which could be a word or some engram or whatever it is, some sort of linguistic unit. If you so each of those has, because they're discrete, they have to go through this embedding matrix, which is basically a big code book. And so for each token, you look up an entry in the embedding matrix that allows you to go from like discrete token space into like vector world, so that you can put it into the neural net. So with that, for different levels of sparsity for the noise, we get like a painting of a group of men. So for some reason, a photograph of a pack of wolves now becomes a painting of a group of men. So we've kind of messed up the network's interpretation of the linguistic information. Then there's this weird, I don't know what this thing is here. It's like some kind of mutated camel in a field. I don't know. And then there's a bunch of soldiers with guns. I don't know why that came around. And then so I don't know. This looks like some artist tools or something. And then you get these textures, and yeah, I wanted to look at like yeah, I actually generated this with a few more frames. This one was kind of interesting because you get like, let me just go to the video. Come on. This thing loves to, and when I save these, it takes like 2 minutes. Anyway,
Richard, if you're using animate, you can set it as an option so that it doesn't play
oh
automatically.
yeah, that it's not the anime, it's those big grids of images which I should just hide. But anyway, yeah, the anime is not causing the problem. Like image
Okay, okay, okay.
collage and a few other things are. But yeah, yeah. So here, yeah, I should have set it so I have the scrubber thing, but I generated more frames. And I also generate past this. So it's like the wolves sort of disappear. There's like, some guy appears and it goes, I don't know. And then there's a scene and some water. I think mountains appear in a second. Yeah, like some mountains. And then this group of men are standing around, like painting, a group of men sort of standing around talking. And yeah, so I call this research artificial brain damage because we're sort of, you know, and I actually did this to my piano network. So whilst it's playing, I randomly put in like some value into the network, and it breaks down in some very interesting ways. But I won't show you that today. Um, and yeah, the second notebook is so here's the same sequence. So it's going from the photograph of pack of wolves, and we're not getting that graceful degradation. We're getting with sparse noise, we're getting we're we seem to be moving like in a more definite direction. In sort of Gaussian distributed noise, it seems we get that graceful degradation. There's a few theories as to like why that might be, but yeah. Um, Here should be playing the 400 frame thing. I think it's maybe just loading or something. No, no, it's still going. Yeah, so I generated more frames and
I mean,
yeah, I wanted to see this figure like what's weird is he sort of only appears in some small range of the global scale value, and there's not much variation to him. So that may be to do with the fact that the network has been sort of quantized to half floats, but also it does beg the question like how like what is stored in these networks? What kind of if you were to explore all possible sort of latent vectors that what are these little pockets of in the space, and how much information is sort of really sort of stored in them? It's not 2 to the 32 or times the number of parameters. It's something less. This is if I go slightly further. So this is a bit more interesting. So let it play around again from the beginning. It goes into textures at the end, but it'll loop around back to the
Hmm.
wolves,
It's
or it
this
should do.
begins with wolves.
This begins with wolves. Yeah,
I.
yeah. So when you go really far out, the network sort of actually what's interesting is it's kind of like these textures would be cool for like use in a video game or something. I'm sure people are applying. Yeah, sorry. So wolves turns sort of painterly, weird figure in the forest. Then you have this background. Then it, water color starts coming back. Um, blah blah blah. Men, but now the photograph, sorry, painting becomes a photograph of a group of men, and then they disappear, leaving only the chairs, and then whatever, and you know. But anyway, this is only affecting the embedding weights. So it's yeah, it's kind of messing with its. So if I said the word like I don't know, phone, it's the first object I could see, and you heard the word like basketball, then that's kind of what's happening to the network, and it's some kind of aphasia, that condition where you have difficulty sort of
Hmm.
understanding language. Um, yeah, and so yeah, Stephen was like,
Oh,
"Why don't we make
oh
a certain
man.
fractional change to?" And I said, "Do you mean applying a global change to all parameters?" So this one is just literally applying some offset to everything. So it's like lifting all of the, that has a sort of different effect. So this is not noise. This is just a constant being added to the whole network, and things get weird. There's like, yeah, let's see, in a few more frames, uh, something, something, something. I have a lot of cool results below when I start getting more surgical and yeah. Let's see. So yeah, the diffusion model has again these submodules. It's called one of them is called input blocks, middle block, output blocks, and time embed or something. So I wanted to analyze those individually, and you get these kind of interesting patterns. Stephen remarked that some of these look like, particularly this one, they look like some of the things you get from video feedback. So that was affecting the input blocks submodule. This one is middle block, and this one uh, seems to do this weird thing where you get wolves tiling the plane. So for some reason, the wolves want to tile the plane. We get all these wolf faces, which looks kind of, it's like a big gang of wolves have appeared out of nowhere and they want to kill you or something. Output blocks, because we're now getting more towards the kind of, the actual pixels, not the internal parts of the network. This is a lot more destructive. So we get all this nonsense. And then there's another layer, another thing called out. And I think that's another sort of transformation. So that on top of the final output. And so that seems to be doing things more in sort of like a chroma space. Although what's weird is we get this green screen where there's a bunch of wolves completely they've been segmented. They're now existing in isolation with no background. And yeah, so and this is me just exploring these with a bit more granularity. Yeah, sorry, here with a bit more granularity. Yeah, you get the cave painting thing, and then it turns into like video feedback type effects. Oh yeah. This one's funny. Hold on. Yeah, this is this weird blob of fluff. Anyway, wolves tile the plane, and then there's like, I don't know what this is, like an old painting, and then like mutant wolf, or like it's bad trip territory. I don't know. Anyway, so then going down further, input blocks has these, I call them sub modules or whatever, and they're just numbered 0 to 11. And so let's look at those. So we get this, we get that. This one is strangely subtle. Here, yeah, like video feedback type things. This is kind of colorful. The wolves go a bit strange, like they're missing heads and stuff. On this one, again, it's like back to interesting sort of textures. This one's very destructive, even from the beginning when the noise is kind of weak. Yeah, there's obviously different sensitivities to the noise. Oh, and then yeah, blocks 9, input blocks 9 seems to be the one that's like, oh, this is the one responsible for some kind of tiling effect. 10 also, yeah, sorry, 9, 10, and 11 seem to all share that characteristic. And I've done it again here with a different sparsity. So that was 0.25, here's 0.5. So we're getting more sparse, and then I did again for 0.75 sparsity. So in some cases you can see it hardly does anything, and it's less destructive. So we can start exploring the effects. So I think we want to go even further down to individual neurons. We're still not down to like the smallest scale, and that's it really. That's all I've done. So and another thing I want to do is maybe try zeroing out different eigenvalues. So take like the largest or whatever. Just try zeroing out different eigenvalues, see what effects those have on the output. Um, yeah. So it's very experimental, but it kind of interesting.
Yeah, this is cool. So okay, so I see the results, and then my problem is I have never really properly studied
Mhm.
convolution networks and this kind of architectures like in detail. So yourself and Nick, you have much more experience on this. What is the sort of neural analogy, like the biological analogy here, like properly? Because I mean, there seems to be clearly some degree of this set of parameters, or this direction of change of parameters. Let me say this region, in some generalized sense, seems to be responsible for more sort of tiling patterns. This one is more responsible for RGB saturation kind of things. This is more responsible for the number of things on the number of blobs of things, right? Things like that. Like, to what degree do you see like a true analogy here in terms of
Mhm.
like the neurological analogy? Like, how much of that do you think is just like pure smokes and mirrors, that we are looking at something and our pattern recognition is firing,
Oh yeah.
and we are seeing that, or how is there how is it that there can be some actual analogy?
Well, the example I gave with aphasia, which was kind of a simple thing, was like, if you're having difficulty understanding words, yeah, I mean that's where like you can sort of relate things to some sort of disease model, I think. But with the tiling patterns, yeah, that's kind of interesting. Like something about some sort of convolution filter somewhere has gone messed up, so it's not able to sort of have this property of like locality anymore. And so, and that's you know that's removing its ability to sort of create some localized structure in the output image. But could that happen to human beings? Yeah, I mean, I wouldn't see why not. The problem is, yeah, in the human vision system, so convolution is like we take some filter and scan it over the whole thing, and there's like this idea of weight sharing. So all the gradients that you compute are kind of getting bucketed into those parameters for the convolution filter. In the human brain, it's not quite like that. We actually have these things which I forget the exact name, but basically it's sort of repeat. We actually have to physically repeat the thing over some domain. In the brain, there's like processes where um, there's growth that has to repeat, whereas in the computational thing, we can reuse the filter, So in that sense, we're kind of breaking the constraints of biology. Biology has to, yeah. I wish I could remember this exact thing, but there's some type of cell which sort of when stem cells sort of decide what they're going to be or whatever, this differentiation process within the brain, and this the brain is sort of self-organizing or setting up these structures. That there's a mechanism that can allow, say, like I mean, because a filter is just some sort of local connectivity pattern to your data, to your input domain or something, right? And obviously, if it was to be achieved in the brain, then you would physically have to disconnect things and then reconnect them, and then disconnect them and reconnect, or and actually physically move things over some sort of receptive field. But yeah, but biologically, all we do is we just grow lots of the same thing. Um, yeah, I mean that's me just exploring the differences and how much you can stretch the analogy of machine learning. But I mean, for example, could we find like this? I don't know. The concept of like a grandmother neuron or something, that there's a neuron or some set of neurons that always fire with some probability when I say the word grandmother, or you think of your grandmother or something like that. Could we find something like that within these networks where, I mean, because like once you have the latent vector and you're sampling in a deterministic way, you always get the same image. Um, but yeah. Or I'm trying to think.
Nick,
Yeah.
what do you think about this question?
It, the analogy kind of reminds me of the similarity with the cortical column, right? It's something like hierarchical structure in your brain. So there's like rarely some actual brain damage that actually only damage some particular layer in this column, right? What usually is what is happening here. You just uh, adjusting some weight of some middle block number 7, right? Or input block. That would be like a damage to one particular horizontal slice for this cortical column, maybe. Right? And it rarely happens when you damage your brain. You kind of damage it to the whole section, like to the whole input part of your unit, not just a particular block. So so this kind of like gradual or slight damage to the physical brain you rarely see.
Mhm.
Yeah.
And when it happens, you basically become a vegetable. So
Yeah, but like, I wonder, is it fair to compare at the following level? So you have a brain, so you have a biological being that is going to develop some kind of brain, like a human or an animal or something, right? And so so the morphogenesis and the ontogenesis of this being is going to give some general features of where connections go largely, and how neurons are going to be distributed largely, and things like that, and how glial cells are gonna, and so to me the analogy there is, okay, you have a neural network that is of this size, right, of these dimensions, this architecture, this rough architecture, and then but once the animal gets going, all these neurons, I mean, after they fully multiply, when the thing is young, they start growing all these dendrites, and they sort of grow back and forth and reinforce and disconnect and create new connections and so on, right? So to me, that's more similar to the training process where you're adjusting weights, but the kind of overall architecture is fixed. Is this a fair analogy to have in mind?
Yeah, I would say so.
Yeah. Okay.
Yeah, we don't see like massive changes, and unless you've like been, what's the brain can sort of rewire and use different cortical regions when there's been damage. Like if you're blind, then your sort of visual cortex gets repurposed, and auditory data starts getting processed in that region, which wouldn't happen in a healthy individual. But those are extreme cases, I guess.
No, but that doesn't contradict what we were saying before, because it's just because, I mean, what I'm seeing here is, I mean, there's something deeply analogous. I've thought about this I thought about this about AI, I guess, for several years, which is, there's something deeply captured here. Like, there's clearly something analogous to what's going on in the brain, where you can systematically recognize that there are regions with functions largely attributed to them, and there's encoding to some degree in the brain and things like that, right? So it seems that, I mean, this quick demonstration that you did, to me, it basically shows that there is like regions of whatever parameter space this thing is doing that seem to encode certain things, right? Like it seems that, for example, I find it interesting when it transitioned to more like a silhouette, and instead of instead more of a perspective like picture. So it seems that after all the training, it was efficient for the algorithm to actually have this as more or less distinct, which is actually how it works in our brain. Like, our 2D processing is quite different from our 3D processing, although everything is visual, connected, blah, blah, blah. Like, we have actually quite separate systems for those kinds of processing. So I don't know, I'm just seeing some pattern, and my worry was like, is this smokes and mirrors? Am I getting tricked into believing that this is the pattern, or is there an actual reason why one should think that this is going on, right?
I was going to talk about co-adaptation. I think it's co-adaptation that leads to this graceful degradation. So there's some kind of redundancy. So as the parameters are evolving during the training, they sort of depend on each other, but in this sort of distributed way. So I think that seems to be why, the sort of uniform Gaussian noise across the whole thing. I mean, because otherwise our brains would sort of fall apart all the time, and we'd be going crazy all the time, and we'd be you know, yeah, or we wouldn't even survive under like synaptic plasticity. So we need some degree of we need some sort of ball or radius around where we are that's kind of a safe region. And
Sure.
yeah, what was interesting, yeah, but actually this big list of things here is all the parameters, and this con stage model is the language model, the transformer. And actually, if you look here, there's like self-attention, these self-attention blocks. So I think what would be interesting is if you do this, it probably will lose the sense of like, because sometimes I'm very surprised. Like I've seen those examples of like cute dog in a house made out of sushi. And it literally makes a cute dog living in a house that's made out of sushi rolls. And I'm like, how does the network understand the relationships of like of these tokens within the sentence and how they relate to each other? And like how does it then know how to make the house and put these little sushi rolls and then put the dog inside, you know? But I saw this example. I think that was a DALI example though. But anyway, yeah, maybe if you sort of start monkeying with the self-attention, I think it will start to lose the relationships of the concepts in the sentence and how they relate to each other, which again is like, you know, if we lost that, then language is kind of out the question. You wouldn't understand, you know, am I talking, the boy saw the man on the hill with a telescope or something? Does the boy have the telescope or does the man have the telescope? That's the kind of classic example of ambiguity in grammar. But we're able to hold both interpretations in our mind. But if you start confusing the and all the grammatical stuff at the fine-grained level, then it's hopeless. You don't understand. Your sentence might be the boy telescope man. Like what? Like it's yeah. So, yeah. I mean, this also reminds me of when I worked in the neuroscience lab. They had this disease model of Tourette's, which is based off of some street drug. There was like this botched street drugs that gave these people like Parkinsonian and Tourette's like symptoms. It's horrible. So don't do drugs, kids. But anyway, these botched street drugs were like giving people these conditions, and then it ends up in neuroscience, and they give them to these poor monkeys. But then those drugs actually sort of knock out like, yeah, and it's quite targeted. They actually do target these areas, striatum and nucleus accumbens and things like that in order to produce these diseases. So that's maybe a justification for doing this very focused thing. And yeah, anyway, that's a disease model of Tourette's. That particular group of systems in the brain, it's quite kind of deep in the brain. So maybe that's a justification for the sparsity and the submodule perturbations, but I don't know. Anyway, I don't want to.
It's very cool. That's very cool stuff.
We'll see where we go.
Right, so should we have a quick look at the progress? I don't have much time left, but I think that's fitting for how long this is going to be. Do you want to show something, Nick, or should I go ahead?
Oh, and maybe you can do it. It's like you will be like testing that out live.
I mean,
So-
I could show some of the progress. I will just mention the progress, and then we can test the one thing that. I mean, we're basically using our viewers' time to test the function. Wait.
You can show the enumeration that you.
Yeah, that's what I was going to show.
Yeah.
Wait, why did I have? There are times where. Oh yeah, it cuts the number of windows for some reason. Okay, so this doesn't work properly yet, but enumeration is working quite well. So at the moment, we have this function enumerate hypergraphs, and it's largely based on the Wolfram physics model sort of function that I think was it Max's?
I think Ed Beck was mostly
Okay.
producing combinatoric functions.
Oh, the combinatorial, yeah. So there is some in the background some algorithm for hypergraph generation, and then we're basically using that to generate the hypergraph objects that our Packlet cares about. And so in particular, these are, as the intention was, these are mathematically mature, sort of mathematically informed hypergraphs. So what are these numbers? So this is the signature of the hypergraph, right? So this is saying you have two binary edges, right? So this is cardinality, this is arity of that arity. So cardinality of the number of those edges of that arity. And this is this is controlling the arity, the cardinality of vertices, right? This argument, and then you have options. So at the moment we have this this way of saying. So this one here is simply generate all the hypergraphs with two vertices. This is exactly two vertices, right, Nick? Yeah.
Yes. Yeah.
So with exactly two vertices that have two binary edges, and you specify that it should be ordered, right? So by default, this is going to list simple connected hypergraphs. So the default is this, right? So maybe I'll say it here. So here you enumerate, you drop any constraints on vertices, and you just enumerate all the hypergraphs with two binary edges. In this case, with ordered edges, right, for the entire thing. So it basically scans all the possibilities, and it's assuming by default that connected is true and that simple is true. So, and that's why you're not seeing any, two vertices and then one thing going round or anything like that, which will be there. And okay, so you can change those options. You can make them unconnected, and I'll show you some examples. You can change the symmetry type of the edges, like this one. By default, everything is unordered at the moment. So if you just enumerate a simple connected undirected hypergraph, that's the only one, right? So that's why you only get that one. So for example, if I don't include a 4 here, I should get the same result, right? Yeah. So these are all the hypergraphs that have exactly 3 binary edges, and these are simple connected. Right, so yes, those are the 3, and then of course when you, for example, set it to order, then you have a lot more combinatorics, and so all these things start to matter. And notice how in particular this is keeping track of simplicity in the right way, which is simplicity is for each kind of vertex, right? Sorry, for each kind of edge. So if you have 2 edges. It's not, simplicity is not checking the number of edges among some subset of vertices. It is checking the multiplicity of types of vertices, of types of edges on those vertices, right? So you would, if they are simple, you would never see 2 arrows going in the same direction between 2 edges, right? So you can drop that, you can drop connected and simple, and then you get all these kinds of things, right? Like the thing you expect, like some floating vertex with some self loop. You get some 3 disconnected edges and all these kinds, 2 disconnected and 1 self loop, like all these things, right? So the entire hypergraph enumeration functionality is there, which was also one of the things that Nick wanted, and it's great. But then it also gives you very controlled mathematically informed hypergraph enumeration, which in particular allows you to do set theory combinatorics or data structure combinatorics in a very controlled way and in a very graphic way as well. So you can always get some feedback. So yeah, I mean, you can. We are testing. I think at the moment, Nick, we don't have a way to do this, right? And this unordered.
What do you mean? Oh, because it can't canonicalize the one of
Yes.
two. Yeah, that's the problem with the algorithm. It's pretty slow.
Right. So at the moment we're still debating how to exactly address the canonicalization of undirected hypergraphs in general. And yeah, we have some candidate solutions that technically work, but we're basically, we are deciding whether, I think we had a conversation about if we go, so we have the canonicalization of the sequential or ordered hypergraphs, And that's why this works perfectly fine. You enumerate the hypergraphs with two ternary edges, simple connected, and that's fine, right? You get some combinatorics. But if these were undirected, there's only two, right? There's this one and there's this one. One second. Actually, just realized. Let me run this again. Oops. Something is not.
We changed this.
Yeah. I was gonna say, yeah. This was missing before, yeah. So yeah, this looks much better, right? So you get four iterations of this. You notice the arrows. Wait.
But we don't distinguish them perfectly graphically yet.
Yeah, the graphical feedback is still, because all these arrows look the same, but they correspond to four different hypergraphs up to isomorphism, right? Like, because you can imagine the combinatorics of oriented.
Basically, the starting and the ending or finishing arrow matters in this case, where it starts.
Yes.
Yeah.
Exactly.
And we have a plan maybe like indicated with the increasing size of this arrowhead.
Yeah, something like that.
So
Yeah. There's some ideas, but then you get this topology, right? This kind of like diamond topology and this sort of bow tie topology. So undirected, it would just be these three, right? You have this, or you have this connected hypergraphs. So at the moment, it's hard to do. Like we don't have a good way to do the canonicalization of those hypergraphs. So we are thinking in particular that it might be worth having a fully unordered algorithm that takes set like data structures and sort of basically set hypergraphs and does canonicalization of set hypergraphs just using some basic set data structure in Wolfram language or whatever, and then we use that for undirected, and we use the existing algorithm for the ordered, and in between we maybe combine them or we see what we do, right? But at least for the two extremes, I think there should be two different algorithms for canonicalization, because it's not obvious. Like the obvious solution, as Nate mentioned in the past, is to take any kind of symmetry property of a hyperedge to encode it as several copies of the sort of the edge under that symmetry property, right? So if you have a ternary
Just
edge,
turn it into unordered. Basically, you turn any hypergraph with arbitrary symmetry to just strictly ordered
yeah,
hypergraph.
exactly.
So by multiplying each hyperedge.
Yeah.
If like completely unordered, you include all the permutations.
Yeah. So there are some problems with that. I mean, that if done properly, that can work, but there are some obvious problems with. I mean, there's the very inefficient approach to higher order stuff, which if you have to actually keep track of that data, it's a lot.
It's going to be a lot of permutations.
Yeah. It grows like n factorial with arity, so it's very bad. So anyway, the point is, we're still working on that, but otherwise the backbone of the enumeration function is there, and it's just a matter of making sure that we get the right objects that we want. So yeah, that's basically on the enumeration front, and then there's the widget. So we're in the process of basically reworking the widget in some sense, and the plan here is to make it as user-friendly as possible and as efficient as possible for, I would say, diagram drawing and sort of explanations and things like that, demonstrations. So basically, I would like to have this widget as a virtual 3D or virtual 2D blackboard, right? Where I can just draw the stuff, put the labels, just copy, and then start applying functions to these things. So basically, I want to write code for functions and options, and I want to input hypergraphs on this widget, and that's how as a hypergraph theorist, or as a network theorist, or as a rewrite system theorist or whatever, that's how I engage with this system, right? With this particular packlet. I don't want to be bracket 1 2 3 bracket 2 3 4 to write the edges. Like obviously you can do that. I mean there's no problem, but ideally, I mean whatever I can do with like some quick strokes, like if I do this and then I change the color, I select this, I change the color, and then and select and go here and do this and do that. Like I don't know, it can be a lot more efficient. Oh, I created some interesting. So anyway, at the moment there's a couple of things, Nick, that I noticed. So for example, if I delete here, well, the clicking behavior, we probably wouldn't need to bore the audience with the clicking behavior, because the clicking behavior is not where it's supposed to be. So delete doesn't work on my computer, but that just might be some Mac Windows problem.
Well, that's backspace works. But I actually maybe it means backspace.
That could be. So let's undo. I don't think so. No. So delete does work, but still has it leaves a trace here. Right?
Oh, we don't want this trace?
We don't.
You want like to delete all the adjacent edges. That's what you want.
No. So you destroy, if you destroy a vertex, like it's quite simple, right? Like the edge is the information of a collection of vertices in some structure, right?
Yeah.
But deep down, it's exactly that collection of vertices. So if one of the vertices disappears, the information of that edge has to disappear, because an edge is never encoding lower order information by the definition of hypergraph, right?
Sure. Well, I don't see particularly why both cases can work or not. Well,
I mean, both cases can work, but the whole point.
like if you remove the vertex, it makes sense for me to just filter out this vertex from each edge. You don't delete all the edges that incident to this vertex.
But that's a very mathematically unnatural operation to do to a hypergraph. It's a perfectly valid computational operation to do to a hypergraph, and it's a perfectly valid editing alteration to do to a hypergraph. But because that's why I prefaced this by saying I want this to be the interface that some mathematicians might want to use, right? It's not so much like if you're going to do editing of hypergraphs, for sure that's an option, and I'm very happy that we sort of flesh out the widget for more general hypergraphs in the future. But if this is meant to be some kind of diagram drawing, which by the way kind of tells you that it should be, because whenever you draw more than I think 10 or 20 edges, it basically breaks down. Like the
Well, actually, have you tried it recently? Because I certainly improved it.
I crashed it today several times, just drawing not that many, like maybe 15 edges.
Well, I'm not sure about the crash and that, but it shouldn't be slowing down as you draw in edges more and more, because now the rendering is local. So at least this is the improvement from the previous widget. So every time you draw an edge, it's kind of local. But before it was like redrawing the whole hypergraph.
Sure, no, this feels faster. So it is faster, but I think at some point it's gonna crash.
Yeah, maybe there's some kind of, I don't know.
No, it is much faster. I mean, the speed is much better for sure. But yeah, I think at some point, I don't know what it felt like. It was some kind of size. But I mean, it's good enough, of course. Like this kind of size for a diagram is perfectly fine, right? I mean, I don't know if I was drawing a lot of. Yeah. Anyway, point is, oh, there it is. That's it. It crashed. Did it? So I got
Yeah.
some Windows errors.
Well, maybe it lost focus, but it still works.
Anyway, I got some crashes earlier. Maybe it was random, but I got a couple of crashes just when there were many things. It is much better in that respect. But there still was some crashing. But anyway, it is a lot improved in that respect. Yeah. So you want to definitely delete the edge with the vertex. I mean that's because that's the whole point of hypergraphs. I mean I was just going to illustrate that if you let me reset. Yeah, now R is not whatever.
Okay.
So if you have this situation, right, and I select, so yeah, the flashing is very nice. This flashing is great. So maybe, I guess you do get control over the frequency of flashing, right?
Oh, I can control it.
Yeah,
It's just set to some constant now, but yeah,
sure, like maybe some faster flashing. But
maybe.
anyway, point is, once you have this, not that, but like the entire point. I mean, I'm gonna make an extremely elementary point, but at least for the benefit of the viewers.
But try multi-selection of edges. Does it work?
It does. It did earlier.
With some button, does it? I don't know what key is it on Windows. Is it Alt one?
I think it worked.
Some of the keys should work.
I think it worked with Control earlier. It doesn't now.
I think I changed it to the Option key. I wonder on Windows which key that would correspond to. Oh, well, maybe it doesn't
Wait,
work.
let me create. Oh, okay. So it's not Control, it's not Shift. Ooh, but why did it make it yellow?
No, shift recovers. Shift recovers. Yeah. That's the old
yeah, that's
behavior.
right. That's right.
That's the old behavior.
No, I can't. It's not Alt, it's not Control. I can't multi-select right now. I could earlier.
No, I've changed the key. The one that the Mac OS supports. I guess on Windows it does not work.
Yeah. But anyway, what I was trying to say is, if you have this kind of situation, I mean, let me change the color. If you have this kind of situation, or this kind of situation, right? We want to think of this as very different. Like, if I delete this vertex here, right?
Yeah.
I mean, let's delete it. Boop. Then you do get some remainder. I mean, ignore the unary ones. But you do get some remainder. Oh, why did this delete? Maybe it was actually multi-selected. You see, I could multi-select here. What is happening? Wait.
Well, for the vertices, it's kind of different.
Is it? It shouldn't be. That's part of the feedback as well.
Not sure.
Oh no, it is doing multi-select.
It
is doing multi-select just by pressing nothing.
On edges?
On edges, I think. Oh no, not on edges. But wait, if I press a
on
vertex,
you can select multiple vertices.
you
And you
can.
can deselect them.
Anyway, yeah.
Well, I
From-
get it. You
Yeah.
should kind of remove all the traces.
Yes. So I mean,
Delete.
yeah, it's as simple as, whatever edge contains that, you want to get rid of that because that information is destroyed. That's kind of the whole point of higher order edges is that they have exactly that level of information. So the moment you go down, they disappear. I mean, you need to encode the lower level information with lower order stuff. Anyway, the other point.
I think I'll do it like for the delete button, but I can bring back that right click of find a deletion, right? If you delete with the right click, it does this trace.
I mean, you can put it in
Delete.
some binding. I don't mind.
Yeah, it's
Yeah, I mean, it's fine to keep it there. So that's not a problem. I mean, the other issue, though, that it's a bit more serious is vertices and edges should behave like the selection of vertices and edges should be the same. Like the behavior should be completely indistinguishable. Like, I mean,
no, I think you wrote it differently. Maybe
I wrote differently, just clicking on empty space, right?
I'm not sure.
Which
Anyway.
yeah, I mean, just I think that description is I checked it again in detail and I think it holds up for what I think should be the implementation. So I did say left click empty space, hold previous selection and create a vertex unselected. So create a vertex, right? Like that's part of the thing that it's not doing currently.
No, it says left click. I'm reading it right now. It says if you click on the vertex, it holds the selection, but if you click on an edge, it unselects the previous edge. So I interpret it as if you continuously click on vertices, it kind of selects all of them. But if you click on the edge,
no. I see. Yeah. No. Okay. So that interpretation is correct. I mean, the implementation is correct under that interpretation, but unselects previous means unselects all, right? But anyway, but that's not so much my worry. I mean, okay, it has to be changed because otherwise it's going to be hard to edit edges. But the point is, when you click on empty space, you should get a vertex. Like, you shouldn't have to press something. Like, why would you want to press empty space and never create a vertex? Like, you'd never want to click on empty space to not create a vertex, right?
well, you create it if you hold the control key, right?
No, not for me.
That's what you said. You said control plus left click on the empty space creates vertex.
No,
Not just left.
the empty space also creates vertex. Like the normal click also creates is there in the text.
Oh yeah, it's
Clicking away in empty spaces always create vertex. That's easy. I mean it's and then it's if you do it with control, it does the same thing. I mean it just does the same thing. Control and click does the same thing for vertices. But then
no, maybe you can see that as a preview, because it selects an empty space. You haven't put the vertex yet there. So
sure. Yeah, but
it's gonna create it when you create an edge.
sure. Yeah, but I think the problem is you might not want to create an edge. And that's the point, right?
Well, then you have a separate button for vertices, right?
But we don't need that. That's what I'm trying to say. Like if you just want to go around creating vertices, you can just click and then unselect, click again, unselect, click again, unselect, right?
Okay.
That's my whole point is that in terms of UI design, I think it's very good to have just one single selection function. Basically, you have an object that you can interact with, you can select it, you can relabel it, and that's it. Like both vertices and edges are going to work exactly the same. Like there's nothing. I mean, sure, there's the extra symmetry information here that's going to apply to edges. So that's where the sort of behavior changes a little bit. But in terms of selections, like okay, I have an element in the screen and I just click it, and it's selected, and it's the same. So the only difference in behavior that I tried to imply with that description was that when I wanted to speed up the process of creating edges. So I wanted to minimize the number of clicks for edge creation, right? Because normally when you start a diagram, you just want edges quickly, right? So that's why I said click to create, select, and hold selection by default. So you click, ternary, click, binary, and so on. It can be quite fast. You don't have to do any extra clicks or presses. But then once you have a diagram, clicking on elements should preserve the sort of that kind of inertia, right? So in particular, if you click on vertices, you hold the selection that you have before, right? And if you click on an edge, you unselect your vertices because you want to probably just edit that edge, change the color or relabel or do whatever, right? So that's the philosophy behind that description. But yeah, anyway.
So maybe we should review the description. Write the actual instructions there.
Yeah.
Let's
I mean, I think, whoops, what's happened? Yeah, so if I share screen 1, I can bring this here. So you can basically see. So this is the intended behavior, just for everyone's context, and yeah, that's what we wanted to do, right? But anyway, philosophically, my entire point is we should have a single selection behavior in a way, like clicking on something just selects it. If you click on empty space, you create unselect. Then keystroke for creation, and as is explicitly here, and the color behavior is also off, but I guess that's just part of the ongoing process. Because at the moment, when you click on something, this palette becomes that color, right? So if I have to change the color here, and then let me just. So if I want it, so now I click this, and I have to change the color. So if I want to create something else, it's that color automatically and something like that, And it's like what I mean is if I click on here, then it becomes black, because I'm selecting something black, So anyway, the color behavior should be more, more sort of like secondary. That once it's selected, it doesn't do anything until you click on the color and things like that. Anyway, small stupid things. It's not very interesting. But that's basically the idea. I mean, the whole point again is that you're able to come here and say, okay, this thing relabel to A, which at the moment we can't because it just does some random edge. I think the first one, some random vertex of that edge, right? Relabeling an edge doesn't do anything. But yeah, the point is you have these objects, you can relabel them. So the philosophy is you graphically input a hypergraph, and via this interface you define labels, right? And labels being in particular color in here, right? Some modifiers. That's kind of the overall philosophy. Like by some efficient click keystroke behavior for just hypergraph creation, and then this interface allows you to select and change color and change labels of both vertices and edges equally, and it has this symmetry behavior. We should probably display that. So if I create, let me reset. So if I create something like this and I say ordered, and I hit E for edge, then your vertex is ordered, right? So if you do same thing for cyclic, I don't think there's a cyclic graphic, but that thing has the cyclic symmetry type inside. We don't have a special graphic there, but if I do ordered 1, 2, 3, then it has arrows, right? So anyway, that's the progress, and yeah, we're actually quite close to having the widget be functional for what we want. Yeah, Nick did some very good work. That's for sure.
Wow, let's see. What time is it at this point?
Well, it's,
Oh, wow.
yeah.
Yeah, okay.
No, ya sabes.
Uh-oh. Yeah. It's dinner time for Carlos.
Yeah, it's my sister's birthday, so my parents are kind of banging on the door.
Yeah, okay. Well, yeah. This has been a fun review. It's interesting to see the work that Richard's doing, now following some of Steven's suggestions. And
That's nice.
so Carlos, Nick, do you guys have not to put you on the spot or not to make you feel as though you need to set a deadline for this, but do you have any expectations regarding the overall hacklet and a final delivery date for it?
Well, I'm thinking that over next week I wanted to go over everything that the packet is meant to be doing. See what because I think a lot of it is quite advanced. See what holes remain. Probably decide on some important things like the canonicalization of undirected hypergraphs and things like that. And then test a few things about rewriting and so on to make sure that. And then the week after, fix all the problems, make sure that we can scale a little bit. And so yeah, couple of weeks kind of time frame is what I'm thinking.
Okay. Well, if you want to see this come to fruition, everyone, you can continue to follow our streams. If you want to find out, what happens to the wolves, do they emerge from the well, we don't know what's going to happen with the wolves. And then we also have some important announcements regarding work on Langlands, and there's some announcements to be made about what Wukash and I are doing over the next few months, but we don't really have time to get into it today. But so there are ongoing developments that I hope you follow in the coming weeks, and so I hope to see you on the streams. I hope to see you all on Discord as per usual. And I suppose it's Friday, so I'll see you guys next week.
Next week.
Thanks, everyone.
Goodbye.
Cheers.
See everyone.
Yeah.